but oppositely directed. The two are oppositely directed. While this is going this way, the other is going the other way. Okay. Or either you say that displacement is directly proportional to the acceleration, but oppositely directed, or that the acceleration is always directed to the mean point. Or, so here, it is either you say that the acceleration is oppositely, or the displacement is oppositely to the acceleration, or the acceleration is always directed to the mean point. Okay. Example. Let me draw some. Please pay attention and then listen. I want to explain. This is a simple pendulum. This is the mean point. The mean point or fixed point. If I displace this in this direction, displacement in this direction, y. But the acceleration is always opposite to the displacement. So while this is displaced at a distance y from the mean point, the acceleration will act in the opposite direction. Or when the body is displaced to come to this point. Yeah, this distance is what we are calling as the displacement. But this is such that the acceleration is always opposite to the displacement. But look at something. Whether you look at it from the right or from the left, you realize that the acceleration A in both situations is directed to where the mean point, the fixed point is. Please, can you see? Can you see?
Yes.
So no matter how you look at it, whether displaced to the right or to the left, you realize that when the object is left, the acceleration of the body is always towards the mean point. Towards the mean point. So it can also be defined as the repeated to and fro or up and down motion of a body whose acceleration is directly proportional to the displacement and directed towards the mean point. Instead of saying but oppositely directed, you can use but directed towards the mean point. Natalie, are you okay? Rayan, Abba, and the rest of you. Are you okay with that explanation?
Yes.
Okay. Now, examples of SHM. The good news is that all examples we made mention of in oscillatory motion are examples of simple harmonic motion. So all the examples we talked about in oscillatory motion are examples of simple harmonic motion. So the motion of a simple pendulum, the motion of a loaded test tube, the motion of the cantilever suspension, the motion of the bifilar suspension. These are all examples of simple harmonic motion. So this is an example of a simple pendulum. Now, when I displace it in one direction and leave it, it will accelerate in the opposite direction. So, assuming I'm using the marker as the mean point around which the to and fro thing must occur, when I displace it and leave it, it will accelerate towards the direction of the mean point. When I displace it in this direction and leave it, it will accelerate. So, this system is always looking for where the mean point or fixed point is. So the acceleration is always directed towards the main point. All right, let's look at some important terminologies used in simple harmonic motion. Some terms, very important terms we'll be talking about. So we must understand terms such as one, displacement. And the displacement is any distance from the mean point or from the equilibrium position. So this is the mean point. Any distance of the body. So whether the body moves from this point to this point or to this point or to all these distance from the mean point A, B, C. These are displacement. So when we talk about displacement, we mean any distance of the body or the object from the mean point or from the equilibrium position is referred to as the displacement. What do you think is the SI unit of displacement? What do you think is the SI? Pardon?
Meters.
Thank you, because it's a distance. All right. Then another important term we want to talk about is two, the amplitude. Amplitude. What is the amplitude? This is an oscillating body. I decide the extent to which it must go. So maybe, let me draw something. Mean point or equilibrium position, MP. I've given it Y amount of displacement. Y amount of displacement. Now, this Y amount of displacement, I must decide. I must decide. So maybe I want this thing to oscillate around the mean point so that its displacement or maximum displacement from the mean point will be 5 centimeters. So I need to displace this so that it will be moving to and fro around the mean point, okay, by this amount, 5 centimeters. So when I displace it through angle, if there's no external factor such as resistance, friction, it would move, and at every point, it will move a distance of 5 centimeters from the mean point, meaning the maximum displacement will be constant. Okay, so whoever is doing the oscillation decides the maximum displacement, okay, about the mean point. So we define the amplitude as the maximum displacement of an oscillating body. So you decide the amplitude of the oscillation. Maybe you want it to move 2 centimeters, 5 centimeters, 10, about the fixed point or mean point. So that maximum displacement which you have given to the oscillating body is what we call as the amplitude. All right. And so the amplitude is the maximum displacement of an oscillating body. What do you think will be the SI unit of amplitude? What will be the SI unit? Oh, Charlotte, Akuya, Yaba, Nanama, SI unit of amplitude.
Meters.
Meters. Because it's also a displacement, but the maximum displacement given to an oscillating body. Then, the third important term is the period. The period is the time taken for an oscillating body to make one complete oscillation. What is one complete oscillation? A body executing simple harmonic motion is such that this is the equilibrium position, rest position. It is equilibrium position because at this position, there is no net force acting on it. Okay. Now, when I move it from here to come to this point, it has to go to the other extreme and come back to give me one complete oscillation. So I'll move it to this direction. This is one extreme. From one extreme to another extreme, and then come back to where it started. That is one complete oscillation or cycle. So look at it. I move it to this direction. If I'm counting the number of complete oscillation, it has to go and come. 1, 2, 3, 4, 5, 6. Anytime it comes back to where I started, starting point, it gives me, okay, so 1, 2, 3, 4. Okay, now, so a complete cycle, or oscillation is made up of 4 parts, 4 quarter parts. What do I mean by quarter parts? From the mean position, 1, this is 1 quarter, 2, 3, 4. So this is the same as starting from here and coming back. I'm starting from the mean point, 1, 2, 3, 4. But when we are counting complete oscillation, it has to go to one extreme and then return to the other extreme. And these are the extremes. This point and then this point are the extremes. But the complete oscillation is made up of 4 quarter cycles. 1, 2, 3, 4. So this is what we mean by a complete cycle or a full cycle. Now, the time taken for an oscillating body to make a complete cycle is what we call the period. So the period is defined as the time taken for an oscillating body to make one complete cycle. So it's moving from here, coming to one extreme, then returning. The time taken to move from here and then come back is a period. Okay, so I start from here. Anytime it comes back, a period, another period, another period, on and on. So the period is defined as the time taken to make one complete cycle or oscillation. Okay. Nanama, what do you think will be the SI unit of a period? SI unit for period. Nanama?
Second.
Pardon?
Second.
The second. Thank you. All right. Another thing. I've explained what a complete cycle or oscillation is. Frequency. Frequency. How frequent are you to school? So frequency is about mode. When we talk about frequency, maybe I've given you X, I have X amount of time, X seconds. Within this X seconds, I want to see the number of complete oscillations that can be made by this body. So a complete oscillation is from one extreme to another extreme and back. 1, 2, 3. So the number of complete cycle and oscillating body can make within a given time. But this particular time, it is often pegged at 1 second. Okay, but actually frequency is equal to number of complete cycles divided by time. But we often peg this time for 1 second. Okay, so frequency is the number of complete cycles, okay, made or complete oscillation made within a second. The number of complete oscillations an oscillating body can make within a second is what we describe as frequency. And the SI unit of frequency is per second. Sorry, the derived unit is per second, and then the SI unit is hertz. Hertz. Please, any question? Any question before we continue? All right. Give me 1 or 2 minutes. I want to drop attendance, okay, onto the platform. So give me a minute or two. All right. So that's it. Now, there is a very important relationship between a body executing simple harmonic motion and a body in circular motion. We'll be applying this relationship in our study of SHM so much. So let's look at that relationship between a body executing simple harmonic motion and circular motion. So relationship between a body executing SHM and circular motion. Hey, circulation. Circular motion. So let's have, this is a body embarking on circular motion. This is the center of the circle. The body starts from a point E, then moves to a point B. And this is the linear displacement, S. Now this linear displacement is directly proportional to an angle described at the center. And this is the angular displacement theta. So clearly all that we are saying is that this body is in circular motion. This body is in circular motion. It has actually moved from a point A to a point B. Are we there? Hello, are we there?
Yes, sir.
Now
Yes,
this body is in what we call uniform, is embarking on uniform angular velocity. This is a body in a uniform angular velocity. In our study of circular motion, we restricted our scope to uniform speed motion, meaning the body is moving at a constant speed, v. This one is about uniform angular velocity. Now, when a body is said to be embarking on a uniform angular velocity, this is what it means. So please pay attention. A body moving with a or in a uniform angular velocity means that at every time t, the body covers equal angular displacement at the center within equal time intervals. So A, B, C, D, E. When it moves from A to B, the angular displacement is theta, and it takes time t seconds to move from A to B. When it moves from B to C, it will describe the same angle at the center, and it will take the same time to move from B to C. C to D, the same angle at the center, the same time. When a body is in a circular motion and it moves, okay, with it describes uniform or the same angle at the center within equal time intervals, then it means that such a motion is uniform angular velocity motion. Please, are you okay with that? With that explanation? Hello, are we okay?
Yes, sir.
yes.
Okay, so we are looking at this body moving with a uniform angular velocity, omega. Okay, so if this is what is happening, then because under circular motion, angular velocity is equal to change in angular displacement over time. When the body moves from A to B, the change in the angular displacement is theta minus 0 over t. because at A, because there's no change in the displacement, initial is 0. When it moves to B, it is now theta. So theta final minus theta initial gives us this. Therefore, we can say that theta is equal to omega t, meaning if I want this angle described at the center, multiply the constant angular velocity omega by the time taken to move from A to B, which is also constant. So I can express theta as omega t. So we clear this and write. And this is where the motion obtained this name, simple. The word simple there refers to the fact that this SHM occurs at a constant angular velocity omega, constant angular velocity. So that constant is what has been captioned as simple. So constant angular velocity or speed, omega. So a body executing SHM does so with this constant angular velocity omega. All right. Okay. So I've explained omega, why omega is constant. Now, this is the vertical y-axis. This is the horizontal x-axis. Let's picture the body to be moving from A, B, C to D. So within the first quadrant, the body is moving in an anti-clockwise. Now, when it is here, we want to always trace the position of the body as it is embarking in a circular motion to its image along the vertical or horizontal, along the y-axis or the x-axis. Let's look at the y-axis first. If the body is at A, its component along the y-axis is 0. It is like in your transformation. If a point is here, x component will be x, but y component is 0. So that's what I'm saying. If the body is here, its image along the y-axis is 0. If it moves from A to B, and I want to trace its image on the y-axis, this is it. I'll read it from here. I'll read it from here. So at A, its image is 0 at the origin, center. At B, its image along the y-axis is this point. Okay, let me say y1. When it moves to C, its image along this y-axis can be traced here. Y2. Now, when it comes to D, its image along the y-axis is the same point, D. So, when we trace how the image along the y seems to be behaving, at A, 0, at B, y1, the value, if it's a numerical value, we realize that it is going up because initially was 0, then y1, y2, and this. So the direction of the image along the y seems to be going up because of the increasing value. Please, are you okay? Is everybody okay with that explanation?
Yes, please.
Okay, so let's look at its movement in the second quadrant.
Yeah.
Hello.
Please, does it mean that the D is not 0?
No, D is maximum. If they are values, 0, maybe 1, 2, 3, 4. So each image at the point D is the maximum Y value.
Okay.
All
Thank
right.
you.
Welcome. Now, what happens to the image as the body, okay, moves in circular motion, okay, along the Y? So let's look at in the second quadrant. This is a point E, F, G. So when it comes here, what is its image along the y-axis? When we trace it, it's like this. F here. Let me create another point before G. So G, H. When it comes to the point G, its image is here. At the point H, what is this image here? What is the image of the body along the Y? What will that be?
0.
0. So if in looking at the image as the body moves within the second quadrant, in numerical terms, will you say that the value of the image is going up, increasing, or decreasing within the second quadrant? Is it increasing or decreasing?
Decreasing.
Pardon? D or in?
D.
Good. It's decreasing because it was at D maximum, then it came to Y something, this and fell to 0. So the arrow for the image along this will be pointing downwards. Let's create about 3 points. We are in the third quadrant now. The body is in circular motion. So it is now here. Okay, so what will be the image here? I, J, K. I will be here. It will be red here. J will be here. And I will be here. Will it be increasing or decreasing? Within the third quadrant, will the image be decreasing or increasing?
I think increasing.
Pardon? Is
It will increase.
Is it increase or decrease?
Increase.
Increasing, but in the opposite direction. This is positive, this is negative. So the arrow will point this way. Because it was 0, then this. Okay, let's complete the revolution. So KL, M, N, then back to A. At L, if we trace the image, we'll look at it here. M, N, and then A again. So how should the arrow go? Must it go up or downwards?
Upward.
So it has to go upward because maximum here decrease to 0. So look at it. For one quadrant of one complete revolution, circular motion, its image along the Y as it seems to be the first quadrant, go up, come down, go up. So when the body continues to be it's involved in continuous circular motion, the image along the Y as it seems to be going up and down like this. going up and down like this. So if a body is involved in circular motion, but its image also seems to be going up and down like this, what does the up and down motion imply? What does it imply? What does the up and down motion of the image of the body imply?
Increase and decrease.
And so that increase and decrease motion of the image of the body, how would you describe that? How would you describe that increase and decrease or up and down motion of the image? How would you describe it?
Harmonic.
Simple harmonic motion. Meaning that as the body involves in circular motion, it is also executing simple repeated up and down motion of the same body or image around O. So when a body is in circular motion, it also describes, or we can also picture simple harmonic motion out of it, and the other way around. And this is the relationship between circular motion and simple harmonic motion. Even in machinery.
Mr. Adrian,
Hello.
please, in the third quadrant, you said that the object is increasing.
The object's position along the vertical is increasing. This is the third quadrant. Okay, because we move from H to I. H, the image was at 0. I, this is how we trace the image position. J, that's it. Then K came to the maximum. So it's like increasing because it starts from 0 and then increase to this value. So increases in the opposite direction. Opposite because this is minus Y. Okay. So increases. I'm listening.
The 0 is greater than all the negative numbers. So how then is it increasing?
No, you see, what we are doing is this. In terms of number line, yes, you have a point. But we are looking at the motion dropping to 0. And then it's increasing a little bit to maximum. Okay, so not in numerical value, but we are looking at its displacement. The displacement got around O was at 0, then it increased to this, increased to this, increased to this. So in terms of displacement, it is increasing.
Okay.
Are you okay?
Yes, please. Yes, please. Thank you.
All right. So this thing is even applied in machinery. Automobile engine, the operation of the car engine is that, you see, the car is filled with fuel. When the key is ignited, fire is set into the fuel to burn. So whilst there is combustion within the engine block, okay, the energy released during the combustion exerts a force on the 4 pistons. So as this burning combustion thing takes place within the engine block, there's a constant regular force exerted on the pistons. So the pistons actually move that up and down repeatedly. Okay, now this up and down movement repeatedly of the pistons is simple harmonic motion. Now, as this simple harmonic motion occurs, there is a circular motion of the wheels of the car. And that is what turns the tire for motion to take place. So we see simple harmonic motion, up and down motion occurring within the engine block, and as a result yields in the revolution or circular motion or rotational motion of the wheels. And that is what moves the car. Okay, So a typical example of circular motion or SHM producing circular motion and the other way round. All right. So there is that clear relationship between a body executing circular motion and simple harmonic motion. All right. Let's put this. Hello, Adoma.
Okay, so does it mean that if anything is moving in an upward and downward form, it means it's undergoing a circular motion?
There is you can trace circular motion out of it too. It's like conjoined twins. They move in pairs. Okay. While there is circular motion, you can picture that repeated up and down motion or to and fro motion out of it, and the other way around too. Okay, so a very important part we've got into, so please pay attention very well. And so we have just realized as the body embarks on circular motion, there is constant motion of the image of the body along the vertical. It is moving up and down around this point O. And so O becomes point O. O becomes the fixed point. The fixed point. Or the equilibrium position. So as the body moves in that circular manner, there is up and down motion of the same image around the vertical. Please, we can also trace what we just saw, okay, along the y-axis, okay, on the x-axis. Either you look at it around y or around o. Both would also indicate or show simple harmonic kind of motion. But I just trace it today. Why? Please, we can equally trace it to the along the x. The body has moved from A to B. And so this describes a certain angle at the center. But we just saw that theta at the center relates to omega t, because omega is constant and the time taken to move from any point is also constant. We are saying theta must be equal to omega t. So we are representing theta by this. Okay. Now, if the body gets to B, its position along the vertical can be traced to this point or this point along the horizontal. So when the body is at B, this is its displacement around O, this distance. So its displacement, okay, around the mean point O, this is it. Its displacement around the mean point O can also be traced to X. As I said earlier, the displacement can be vertical or horizontal. Now, if this is Y displacement, this distance is also the same as this distance. So if this is y, this can also be y. And this y is perpendicular to this. Just as this displacement of the body is this. Now, I want to use trig to have a relation for y in terms of another point. What is this distance? From the center to the circumference. What is this distance? What's the name given to this distance?
The hypotenuse.
So in terms of circle, how would you, yes, the hypotenuse, but in terms of circle, what special name will you give to this?
Radius.
Exactly, y. Oh, sorry, r. Now, if the body is executing simple harmonic motion, that repeated up and down motion of the body around the center O or mean point O, from the center to this point or to this point, how will you call this distance? From the center to where these are extremes. One extreme and then another extreme. Meaning the body is doing up and down motion about O. So its movement is between these two extremes. How would you call this distance from the center to one extreme? Yes, anybody? Anybody? Okay. This distance we will call as the amplitude, because this is the maximum displacement of the body. So this is the amplitude. This is another amplitude. Because we have two extremes, we also have two amplitudes. So this is another amplitude, but negative. One along the positive, one along the negative. Okay, what did I say about amplitude? An amplitude is the maximum displacement of an oscillating body. Please, are you okay?
Yes, please.
Yes.
Good. Good. So that is the amplitude. So when the body is executing simple harmonic motion, the maximum displacement from the mean point O is known as the amplitude. Now, this distance from the center to the circumference, because this is circular motion, we are saying this is equal to, this is known as the radius. But class, do you think this radius will be different from the amplitude? Is the radius different from the amplitude?
No.
No.
No,
They are
please.
they are the same thing, but we are giving them different names for what they are doing. Because at B, the body is doing circular motion. We are saying let the distance from the center to the circumference be called radius. Because the body is moving up and down around O, we are saying that let the distance from the center to any of the extremes be called amplitude. So it's the same thing, but we are giving them different names for what they are doing. So we can say that R is equal to A. Radius is equal to amplitude. Does it make sense?
Yes, please.
Yes.
Okay. Okay. So these are the technicalities involved here. So please pay attention. So R is equal to A. Now, if R is equal to A, I want to get an equation for the displacement Y of the body in terms of time. So when I take sine of omega t, sine omega t is equal to the opposite y over the hypotenuse, which is either A or R. When I make y the subject, I have A sine omega t. Maybe I'm interested in x. So I want to have a beautiful equation for x. If I take the cosine of this angle, cos omega t, this is equal to the adjacent, which is x, over the hypotenuse, which is either R or A. X, therefore, is equal to A cos omega t. And we call these two equations the displacement equation. The displacement, these are the displacement equation or function of a body executing simple harmonic motion. The displacement equation or function of a body executing simple harmonic motion. What does this equation or function actually mean? This is what it means. You see, as we analyze the body as the body's repeated up and down motion around the center O, we concluded that, okay, then as the body is in circular motion, we also see the image of the same body moving up and down about the center O. So this equation will help me or help us determine the position of the body along the y-axis at any time t. At time t is equal to maybe 0 seconds. Where is the body, or what is the displacement of the body? I'll use this equation to determine along the y-axis or along the x-axis. Example. In terms of, don't forget, omega t is equal to theta. So it also means that this equation, I can also write it as y is equal to A sine theta. Are we okay? Are we okay?
Yes, please.
Now, when the body is at A, theta is equal to 0. When the body moves to let me name it with AW till Z. The body at A, theta is 0. At W, what is theta? At W, what is theta?
90.
90. At Q, what is theta?
180.
At Z,
270.
270. And back to A, theta is 360. Now, when the body is at A, can somebody guess the displacement of the body along the vertical, along the y-axis? When at A, can somebody guess the displacement of the body along the y-axis?
Please, can you show it like on the diagram? I don't get you.
The body is here at A, where theta is 0 degrees. Now, when the body is at A, can somebody guess the displacement of the body along the y-axis?
There's 0.
Pardon?
There's no displacement. See, there's no displacement.
So displacement is 0, right?
Yes.
We can
Yes,
use
please.
this. This is what we can. Y is equal to A sine 0. And what is sine 0? Sine 0 is 0. So telling us that, oh, when theta is 0, the displacement is 0. When the body moves to W, because theta is 90, we have Y is equal to A sine 90. Sine 90 is 1. And so Y is equal to A. What is A? What is A?
The radius.
No, amplitude. Fine. Charlotte, you are not wrong to say radius too. But when we are talking about circular motion, we talk circular motion radius. Then simple harmonic motion amplitude. When the body is at Q, where theta is 180 degrees, what's the displacement along the vertical? When theta is 180.
0.
It's 0. So it means that when the body moves and then comes to this point, there's no displacement, okay, of the body around or compared to the point, the center O. There's no displacement. Now, when the body moves from Q to Z, what is the displacement?
Minus A.
Minus A. And minus A is the amplitude in the maximum displacement, but in the opposite direction. Is that okay? And then when it comes back to A, where theta is 360, what is the displacement?
0.
0. So over here, when the body is here, when you compare its position to the center, it hasn't moved. It is at the same point as the origin or the mean point. So the displacement is 0. Please, are we okay? Is everybody okay here?
I don't get why the 180, the displacement is 0.
Okay, Charlotte, you have moved from here and to this point. Displacement, we are comparing. What did I say about displacement? When we talk about displacement, it is the distance of the body from the mean point. The mean point is here, O, and you are here. So if you are here, when we are comparing you and then the mean point or the center O, is there any difference between the two positions?
No, please.
No. That is why it is 0. Are you okay?
Yes, please.
Now we can also describe the same thing using this. This time, don't forget, we change. So we are looking for what we've just discussed. We were discussing displacement with angles, theta. But because theta is equal to omega t, we can also describe the displacement of the body in terms of time t. So when you equate y to be equal to a sine omega t, you are expressing displacement with respect to time. When you have y is equal to a sine theta, you are expressing displacement with respect to angles. Both, okay, both of them would equally play out nicely. So let's see how we can connect displacement to time. So omega t. Okay. Omega t. This time, we are going to express the points. Is everybody active? Natalie, Kim, and Ryan, Carl.
Yes, sir.
Herbert. Herbert has gone to sleep. Ekwiadoma.
Yes, dear.
Kali.
Mr.
Okay. So, A, W, I said Q, A, and Z. Okay, instead of Z, let me make it P. And back to, when it comes back to A, is Z. Now, from start, okay, let me start from the origin. When it moves from here to here, and then comes back, we have a complete cycle. And the time taken to make one complete cycle, what's the name given to it? What's the name given to the time taken to make a complete cycle?
Period.
So capital T. I said a complete cycle is made up of how many parts?
4.
4 parts. So this is what we are going to do. When it moves from O, we are looking at SHM, repeated up and down motion. When it moves from O to W, from O to W, we have the time taken will be quarter of the period. From W to O, the same time, but it will be half of the period. From O to P, the same time, but this will be 3/4 of the period. And then from P to O, it will be T. So quarter, half, 3/4, and a period. So we are only dividing the time taken to do this into 4. And each quarter is of the same magnitude. So in all the 4, it takes the same time. Are we there? Are we okay?
Yes, please.
All right. So when...
Miss Stadium.
Hello?
Please, what is the P to O?
Pardon?
The P to O, the last one that's the P to O. Right. Where's the P to O?
Where is the P? Oh, okay. That's it. I covered it.
No, I meant like on the diagram. Where's the P to O?
Is that what is the P to O?
I said, where is the P to O on the diagram? Like,
we are looking at the body moving from O to W. O to W, then W to O, O to P, and from P back to O to give us a complete cycle.
Sorry.
Are you okay?
Yeah.
So from OW, but before we even go through it, when the body moves from O to W, what is the displacement? When the body moves from O to W, what is the displacement? A.
It's equal to amplitude.
It's equal to the amplitude. Thank you. So when you move from O to W, Y is equal to, Y must be equal to A. Let's see if when we use time, we'll get the same thing. Y, so we are expressing displacement in terms of time. So we are talking about at when T is equal to, let's begin from 0. When T is equal to 0, when we are here, what is the displacement? Now, when T is equal to 0, what do you think will be the displacement? When T is 0, what will be the displacement?
0.
Oh, class. When T is 0, what's the displacement?
0.
0.
No.
The rest of you are not sure. You are not responding. It's 0. Because when T is 0, we are just here. Okay. So when T is equal to quarter of the period, meaning we've moved to OW, Y is equal to A sine omega times T is quarter of the period, T on 4. Now, under circular motion, we saw that angular velocity is equal to either 2 pi f, which is also the same as 2 pi over t. So substitute this in place of omega. You have y is equal to A sine 2 pi over t times t over 4. So you have A sine pi on 2. What is pi on 2 in degree? What is pi on 2 in degree? Hey, what is pi on 2 in degree?
1.578.
In degree. Pi
180
on 2.
degrees.
180. Pi 180. Pi on 2. Pi on 2 in
60 degrees.
Listen to the question again. What is pi on 2 in degree?
90 degrees.
90. Pi is 180. 2 pi is 360. Pi is 180. So pi on 2 is 90. So when you change pi on 2 to degree, you have A sine 90. And because sine 90 is equal to 1, y is equal to A. Just to prove what you preempted earlier. So when T is equal to quarter of the period, the displacement is equal to the amplitude. Now, what happens when T is equal to half of the period? Yes, do confirm it for me. Put them in and confirm. When T is equal to half of the period, what is the displacement?
0.
Is 0. Is 0. Let's do it. So y is equal to a sine 2 pi on t times half of t. This and this cancels. This and this cancel. A sine, you have pi. And pi is 180 degrees. Therefore, and sine 180 is 0. So y is equal to 0. And this is what it means from the diagram. Meaning, we were on O to W, then W to O. Displacement is 0. Okay, O to P. Inshira, what do you think will be the displacement, Inshira? O to P. Inshira. Hey, Inshira. Okay, Yaba. O to P. Yaba.
Is minus A.
Minus A. Good. So, please confirm. Use substitute the time into it. O to P. The time is 3/4 of the period. So confirm for me. Is it confirmed? Hello, is it confirmed?
Yes.
Yes, please.
Okay. So this is how to connect displacement to time and displacement to the angle. Meaning, once the body oscillates up and down around O, we can use this to determine the displacement of the body at any time t or at any angle theta, either along the vertical or along the horizontal. Okay, so if you want the displacement of the body along the vertical, use y is equal to a sine omega t or sine theta, a sine theta. And if you want the displacement along the horizontal, use x is equal to a cos omega t, meaning that the body's position is always changing whilst the body oscillates. Its position is always changing. It doesn't have a constant position. It is always moving, changing with time or angle. Okay. And anybody whose position or quantity changes with time, okay, and it is repetitive, that thing is repetitive, okay, we realize that the body changes position between the extremes, between the two extremes, okay, and the same thing is repeated on and on, okay. Now, anybody that exhibits such behavior, okay, explains a harmonic function. Harmonic function. So harmonic functions actually changes with time. Harmonic function changes changes with time and is repetitive. Harmonic function changes with time and is repetitive. So this up and down or to and fro thing, okay, changes with time. The displacement changes with time, and that thing is also repetitive. It is repeated all the time. So the reason for which in SHM, simple because omega is constant. Any harmonic function has a constant angular velocity. It is harmonic because this some quantity or some quantities such as displacement, velocity, and acceleration changes with time, and it is repetitive, hence harmonic. Then, because this is a motion, so this behavior explains whatever we see as simple harmonic motion. Ama?
Mr. Adria, please, you said it is harmonic because displacement, time, and I didn't hear the third quantity.
It is harmonic because, you see, this, whatever we saw changes. The display, you've seen displacement. Displacement changes with time. And this change is also repetitive. So you see its displacement, its velocity, and its acceleration changing with time. And it is repeated at all. Okay. The reason for which we said this is harmonic.
Okay, sir.
All right. And so we have the displacement equation of a body executing simple harmonic motion. Now, any system that is repetitive can be expressed as a sine function or cosine function. Any system that is repetitive and changes with time can be expressed as a sine function or cosine function. Either function or equation. So if you see an equation expressed as a sine or cosine, then it means it is something that is repetitive or changes with time. So we can even express whatever we are seeing, okay, as a cosine function to indicate that simple harmonic motion thing. So let me draw that for you. A body executing circular motion, but we can also see simple harmonic motion out of it. So we are plotting a graph of displacement y, a graph of displacement against time. Now, the time taken to make a complete revolution is a period. So, but a complete revolution is made up of 4 equal parts. So, quarter of the period, half of the period, 3/4 of the period, and then t. So we are looking at displacement along the vertical. So using y is equal to a sine omega t. This motion occurs, okay, between the extremes. So we have the maximum displacement A, we have the other maximum displacement, which is the amplitude minus A. Now when t is equal to 0, the displacement of the body is equal to 0. When t is equal to 1/4 of the period, we got the displacement of the body equal to the amplitude. So this time goes with a displacement equal to A. So this y is equal to A. Then at t is equal to 1/4 of the period, y is equal to 0. So at t, half of t, displacement y is equal to 0. At t is equal to 3/4 of the period, we have the displacement equal to negative of A. So this time would go with displacement equal to A. Then at t is equal to t, the displacement is equal to 0. So I'm only plotting for one cycle. So let's join the plotted points. So for one cycle, this is how the body's displacement is changing with time. And it's a sine function telling you that this is a harmonic function. I can draw it for 2 cycles. When this has gone, okay, 1, 2. This is just, okay, from the mean point moving to one extreme to another extreme and coming back. But I can also draw it for 2 cycles, 3 cycles. For 2 cycles, 1/4 t, half t, 3/4. Okay, and then t. So we are adding 1/4. So 1 plus 1/4. What is 1 plus 1/4? Who is doing it for me? 1 plus 1/4.
7/4.
No. 5?
5/4.
Yes. I don't remember.
Sorry.
1/4 plus 5/4.
3/2.
3/2. 1/4 plus 3/2.
7/4.
Abba. Adoma.
Yes, please.
1/4 plus 7/4.
2.
No, 2t. Yes. So I'm drawing it for 2 cycles. So when t is equal to 3/4, this will be equal to A. What the displacement will be equal to A. When t is equal to 3/2t, the displacement will be 0. Confirm. when t is equal to 7/4t, the displacement will be equal to negative a. I hope you are confirming. When t is equal to 2t, displacement is 0. So for 2 cycles, that's how it will go. So look at it, repetitive. 4 cycle, another 4 cycle. So it's a repetition of the whole thing. Natalie.
Sir, please, as it is repetitive on the y-axis, would it be the same on the x-axis?
Exactly. You can do it at your free time. Do it for x-axis. Using x is equal to a cos omega t. It will be the same. Okay. Now, what I'm saying is that because the displacement along y and x is repetitive, the reason for which we are expressing displacement as a sine or cosine. So when you see a sine, something expressed as a sine or cosine, it simply means that that quantity is repetitive. Natalia, are you okay?
Yes, sir. So please can I give you a question where you'll be asked to draw the graph with both the x and y axis.
It's
Going to
one.
look complicated.
It's one at a time. It's just one.
Okay.
Either draw it for 1 cycle, 2 cycles, okay? Well, using displacement along the y-axis or x-axis.
Okay, thank you.
Okay, so we are creating a graph of this is simple harmonic motion out of a body executing circular motion for 2 cycles. For 2 cycles. For 2 cycles. Is everybody okay?
Yes, sir.
So when you are doing it for 2, 3 cycles, please the interval must be the same. Because initially what I did, I had smaller interval. The reason for which this graph it's narrowing, shrinking, because I don't have the space again. So if you do it for 2 cycles, 3 cycles, make sure that because the intervals of the time involved for the period is the same, ensure that it is the same. And you have a very beautiful sine graph. Is that okay? All right. Another important thing I want us to look at, and that is, we see the body moving up and down either along the vertical or along the horizontal, meaning the body is always not at rest. It is always in motion. Now, if a body is always in motion, what will you say about the body's velocity? Anyway, will the body have some velocity at all? If it has, its displacement always changing. Will the body have some velocity?
Yes, please.
Why? Why would there be a velocity?
Because it's moving at a certain speed in a given time.
Anyway, that is Charlotte's view. And thanks for the view. Stephanie, let me hear your voice. Can we talk about the velocity of the body? Stephanie, can we talk about the velocity of the body? Yes, just yes or no. Oh, Stephanie.
Yes, sir.
Yes or no? But if yes, why? Why can we talk about the velocity of the body? Why can we talk about the velocity of the body?
Mr. Adria.
Yes.
The change in displacement with respect to time brings about the velocity.
Exactly. That's the point. Because the body's displacement changes with time, okay, it will amount to velocity of the body with time. Because what is velocity? Velocity is the rate of change of displacement with respect to time. So the moment a body's displacement changes, there must be velocity. So the next point to look at is the velocity equation or function of a body executing simple harmonic motion. The velocity equation or function of a body executing simple harmonic motion. And it matters because the body's displacement is changing with time. Please, is that okay? Len, are you there? Len? Or Len did not come today?
Please, I'm here.
Okay. So the velocity function or equation of a body executing SHM. Since velocity is equal to the rate of change of displacement with respect to time, it means that if we want to determine the velocity of the body at different time, when t is 0, t is quarter of the period, when t is 3/4, half, and so on and so forth, we must differentiate the displacement function with time to get the velocity. Okay. So to obtain velocity equation with respect to time, differentiate displacement function or equation with respect to time. And that the mathematical thing is what I've written here. To get V, we have to see how D changes with time. So the differential of the displacement function along the Y means we are looking at displacement along the vertical. So A sine omega t. Now, you haven't done differentiation in maths. So here I'm going to apply mathematics so that we can determine the expression for the velocity. It may be new to you, okay? But in fact, I must apply this mathematical concept so that we can get our velocity, okay? Now, this is a function of a function. So the differential of this, I'll give it to you. Later you read around. Okay, let your math teacher introduce you something on differentiation of trig function so you understand this. So if I have to differentiate this, this is a coefficient. It will not be affected in the differential. So it will come out to multiply. So I have to deal with the differential of sine omega t, because this is a coefficient. It's like the normal 2, 3, 4. It will not be affected. So a times this. This one too, I have a function omega t in a bigger function sine omega t. So when you have a function in another function, you differentiate all of them individually. So we have a smaller function sine omega t within a bigger function sine omega t. So the differential of this will be the differential of the smaller function omega t times the differential of the bigger function sine omega t. Now, when you differentiate omega t with respect to time, this is the same as a coefficient. Don't forget, this is a constant. So it would also be pulled out. So we have omega out dt over dt. When you differentiate sine omega t, it is equal to cos omega t. And so this and this will cancel out, meaning the differential of what I have here will be equal to a omega cos omega t. So when you differentiate a displacement function along the vertical, this is what to get. The amplitude times the constant angular velocity times cos omega t. I'm borrowing mathematical concept which you have not been taught. I know it will be something, okay? But if you can plead so that your math teacher can quickly take you through differential of trig function, because we are applying it in physics, it will do us a lot of good. At least 30 minutes, he can explain something to you. Please, is that okay? Is that okay?
Yes, unless you talk to Mr. Akman for us.
Oh, you can tell him. Just 30 minutes, he can help you out. Meaning that if you are looking at differential the velocity function along the vertical, it will also be different. So this is what we've done along the vertical. When the body oscillates up and down along the vertical. Along the horizontal, this is what will happen. We have x is equal to a cos omega t. This is the displacement function along the horizontal. So the velocity function would be the differential of this with respect to time okay. Now, as we apply the A is a coefficient, so will not be affected by the differential. A multiplying so cos omega t. Now, this is also a function of a function. smaller function omega t within a bigger function. So you differentiate the smaller function and differentiate the bigger function. So the differential of this would also be del dt of the smaller function omega t times del dt of the bigger function cos omega t. So you differentiate the smaller function and differentiate the bigger function. And this will be equal to A here to omega is a coefficient. So dt over dt times, when you differentiate cosine, it is equal to a negative sign. The differential of cosine is equal to minus sine. I think I'll send this basic differentials of trig function to you. Differentiating sine will give you, the cosine will give you this, okay? And that would help a little bit. So you have V is equal to A omega, there's a minus. Minus A omega sine. So for velocity function along the y, this is it. Along the y, when the body is oscillating along the vertical, this is it. Then along the x, this is it. What does this mean? It means that this will help us calculate for the velocity of the oscillating body at any time t. One cycle, starting from 0, the mean point, getting to one extreme, coming back to 0, moving to the other extreme, and coming back. One cycle, either along the vertical or along the horizontal. Now, let's quickly apply this to see why this would be important. A, B, C, D. This is the mean point O. If the body is oscillating vertically, when the body gets to one extreme B, what is the velocity? What is the velocity at this point? Yes. Can somebody predict? Can somebody predict the velocity of the body at B? You are just trying, so you can't. Can somebody predict the velocity of the body at B? Yaba, try. Equia, try. Nanama, Len, Amma, Stephanie, Adoma, Effie, Herbert. Oh, okay. Okay, so who is predicting? When the body is at B, what do you think is the velocity of the body? Charlotte, try. Okay, Amma.
Except this, I think the velocity will be 0.
Amma, why do you think it's 0?
Except this, when it starts moving from point A and it reaches B, it stops. Like, yeah, it stops. So like there's no motion occurring. So
Amma, you are right.
velocity.
You are right 100%. So when this body is moving up and down between point B and D, meaning if it gets to this point, it will stop. Meaning as it's from A, its velocity towards D will be decreasing. By the time it gets to B, it has decreased to 0. Okay, then increasing. Then from O to D, it will also be decreasing. By the time it gets to D, it has decreased to 0. So at the extremes, the body's velocity is 0. The reason for which it stops. So please put that down. At the extremes, the velocity of the oscillating body is 0. This is the reason why it stops. The body stops. Lane, okay? So V at the extremes, 0. 0. So we say that the oscillating body has minimum velocity at the extremes. The oscillating body has minimum velocity at the extremes. Where does the body have maximum velocity? And let's use the equation to see. For when it moves from O to one extreme here, what is the time taken to do that? Quarter of the period. In terms of angle, it has moved through an angle of 90 degrees. Theta is 90. Don't forget, we can always switch from omega t to theta. Are you there, class? Are we there?
Yes.
So let's use time. When the body moves from this to this, t is quarter of t. So V is equal to A omega cos. Omega is 2 pi over the period times the time is quarter of t. Quarter of t is t on 4. So we have A omega cos pi on 2. Change pi on 2 to degree. Let's change pi on 2 to degree. Yes. Yes. 90. So we have cos 90, which is equal to 0. So when the body gets to the first extreme, positive extreme, velocity is 0. Please, let's confirm when the body comes to this point. Would move to D. And the time is, this is quarter of the period, half, 3/4. So when it comes to D, the time taken is equal to 3/4 of the period. Let's use the velocity along the Y to confirm the velocity at this point. So do it for me. Are we through? Hello, are we through?
Yes, please.
So what did you get for velocity at D? Oh, what did you get for velocity at D? Hey, 0. Okay. So please note that for a body executing simple harmonic motion, velocity at the extremes is equal to 0. Okay. We'll look at where does the body have maximum velocity and all that on Monday. My my earpiece has actually come to its dead end. It's giving me that signal. So
Please, Teja.
hello, Aduma.
Please, I want to take a...
Pardon? Charlotte, speak. My earpiece is going off. Okay, so Charlotte, if you have any question, send it to me to address it for you. So girls, this is why I draw the curtain. Hey, sorry, ladies and gentlemen, this is where I draw the curtains on today's meeting. Okay, please upload the video as usual. Have a nice weekend and take care of yourselves. Is that okay?
Okay.
Thanks.
Yeah.
Bye.
Bye-bye.
Bye.